Today I want to tell you about how to use serverless infrastructure and how to architect it for data science projects. How data science process usually looks like. Basically, you start with a business case where you need to understand your objectives, you gather understand where you can get data, and you define metrics. Next, you get data, you have to clean it. Usually it's one of harder steps. After that, you architect the model and you try to train it. Next, you have to operationalize it and put it into production. And then you give the results to customers and try to gather feedback. And then you probably have to update the model. So actually, the last 3 steps is a more like iterative process. You get feedback, you update model, you deploy to production, get more feedback. So the challenge here is that we have to have a flexible infrastructure so we can actually start early to get some early results. Basically, the takeaways which I want you to have after this talk is to how this infrastructure allows you to tackle these challenges, how different examples of architecturing it, and use cases, do's and don'ts. Serverless is a pretty broad, has a pretty broad meaning nowadays. And basically, there are different ways how you can deploy your application. Starting from on-premise, where you control the whole stack, to functions as a service, where you control only functions or code without any container, and so on. In my talk, I want to specifically focus on these 3 stacks: container as a service, platform as a service, and function as a service. Specifically, because in that way, you don't have to care about VMs at least. So it's already provide a good way to deploy application. Let's start with describing them. So functions as a service, it's like AWS Lambda, Google Cloud Functions, Azure Functions. You just define code and libraries, and you are able to deploy the application. Container as a service is a little harder. You have to define Docker, but once you have a Docker image, the service itself will handle it. It's something like AWS Batch, AWS Fargate, or Google Cloud Run. And platform as a service, in my specific case, I mean orchestrator, meaning that service which controls FAS and CAS. It's like AWS Functions and Azure Logic Apps. Because one of the defining features of function service and container as a service, they're stateless. So there is no state on any of them. So platform as a service, like step functions, they have to keep the state. Let's start with function as a service, just like how it works. Basically, the service, you define code, libraries, and configuration. Next, when service receives trigger, it could be change in your database, in S3 file store, API request, so on. It will take a container from the container pool, put your code, libraries, and everything inside the container, process the request, and produce the response. After that, it will keep this container up for 4 to 5 minutes, plus or minus. And if new request will come, it will process it with already existing container. Basically, that's the difference between cold logic and warm logic. So it's cold container, warm container. What can act as Lambda triggers? Basically, a lot of stuff from database and file store to API to queue like SQS, and Lex as a basically platform for chatbot from AWS. So it's very convenient. You don't need to know Docker to deploy it. It's very easy to integrate with other AWS infrastructure. It's scalable, so you don't have to work on it, and it's relatively cheap. It's cheap if you have low quantities, but it doesn't have any economy of scale. So under my personal opinion, under 1 million requests, Lambda always wins. Between 1 million and 10 million requests, probably on par, depending on how you would make your cluster. More than 10 million requests per month, you probably should switch to cluster. Also, it could be very hard to log Lambdas, and it could be very hard to debug it locally. And also, the warm logic, which I told you about earlier, it's impossible to monitor it. You cannot know how many warm containers do you have at current time. AWS doesn't provide this kind of information. So next is container as a service. Basically, what I mean by container as a service or serverless cluster. Basically, it's either cluster which scales with your consumption automatically. You don't have to configure cluster itself. And basically, it scales based on your job queue. Or it creates a separate VM for each of your jobs in your job queue. Basically, the first example is AWS Batch. The second is AWS Fargate. Let's compare basically them with Lambda, like to understand like how they're different. Basically, Fargate starts pretty fast, but it only limited to CPU instances, while Batch can use any instances you can on AWS. The problem, though, is that it starts pretty slow, but it can utilize spot instances, meaning you can have very cheap instances. Basically, if we're going to compare pricing, we will see that basically AWS Lambda is the most expensive in terms of computing power per hour. Basically, why is that? The thing here to remember is that pricing in Lambda is per 100 milliseconds. And although like pricing for Fargate and Batch per 1 second, which doesn't sound like a big difference, the problem here is that minimum is 1 minute. So if, for example, your workload have like processed in 40 seconds, you will be better with Lambda than with Fargate or Batch, because you will have to pay full minute. So as you can see, if you have spot instance, it will be the cheapest option. The Fargate you can also customize, so you don't have to use all CPU and all RAM. You can have like half CPU and a lot of RAM, or a lot of CPU and not a lot of RAM, and it could also save you money. And let's compare like GPU prices. Fargate and Lambda doesn't provide GPU. The only way to get it through like alternative way is SageMaker. So SageMaker handles a lot of stuff for you in terms of infrastructure, but it's the most priciest option. As you can see, Spot allows to be like almost 5 times cheaper. And finally, platform as a service, specifically cloud-native orchestrators. As we're dealing with functions as a service, containers as a service, it's microservice world. There are 3 ways to connect services between each other in microservice world. It's either API requests, event query between services, or orchestrator will handle the whole workload and calls each service separately. Basically, REST API and event query, they're good because they're cheaper options. It's harder to trace. They're good for their cases. Like if you have long processes, you're better with event query. If with short processes but synchronous, it's better API requests. But orchestrator is extremely useful because it allows you to trace and make a complex logic, and it's easier to debug your workflow. So if we're looking specifically at why cloud-native orchestrators, is because they usually have native support for function as a service and container as a service, so you don't have like write your code to call them. It has central monitoring, logging, tracing, and it scales. There are 2 kinds of orchestrators. It's AWS Step Functions, which integrates with other AWS services, and Azure Logic Apps, which has even wider integrations, and it even has dynamic parallelization. If we are speaking about specific features of orchestrators, basically you define graph-based description, how your workflow looks like, and then you basically define task on each step, and you can make custom logic. So in case, for example, step failed, you can retry it, depending on error type, which it produced, and so on. Or you can have parallel execution, branching out, or you can have like loop logic. So basically, you can be pretty flexible in terms of it. So having said that about serverless infrastructure, what I define by serverless approach for data science or for any other task? We're using AWS Lambda for short parallel processing. We're using AWS Batch for heavy processing, using GPU instances, something like this, and Fargate for long-running processing. And we use step functions to wrap up all of them. So some example patterns, which combination of these 2 services allows to get. First is that like if you have some old cluster, you can basically wrap it up around using orchestrator and lambdas, and you can basically have a timeout, error handling, retry logic, so you basically can enhance your workflow which happens on cluster. Second is that basically you can have a parallelization of workload which happens on cluster, and you can make a custom logic for each branch. So your parallelization won't be like trying to fan out like 10,000 requests and trying to gather them. You will have logic for each one of these branches. And finally, it allows to have this kind of like canary deployment in a way, or where you have old and new kind of deployments, because orchestrator can switch traffic and basically gather data, produce results, and so on. Let's switch to specific data science project which we have to deal in real life. So let's start with data pipeline. So the usual issue with data pipeline is that you have multiple sources where you want to gather data. You have different frameworks, some frameworks for image processing, for text processing, so on. And you want to be able to scale automatically because like a lot of data came in at like in 1 minute, and you want to process everything in parallel. So here, basically, it allows to kind of have your combination of heavy GPU or CPU processing with having parallel processing nodes, and allows to have different modules with different frameworks. And it definitely works if you need to scale fast, if you need custom logic, or if you want to have customizable pipeline. So here is a repository. I will show you demo at the end of presentation, which will use this repository. Basically, it allows you to deploy step functions with Lambda, with batch and Fargate in one deploy. And basically, you can define logic. So in one file, you can define basically execution graph of step functions and define each node, and it will deploy it. Next, machine learning, deep learning training pipeline. So the issue here is that GPUs are pricey. And if you, for example, have you define your model and you need to prepare your model, let's say for a new customer, and you want to check like 10,000 pairs of happy parameters, and you want to try to do it in parallel, or if you want to have feedback loop from person, so you want to have like semi-automated logic of your workflow. Then basically it allows us to kind of handle parallel training on the AWS batch. It can handle error on each of them, and it allows to use spot instances, meaning that the training part becomes extremely cheap. And if you, for example, have like 5 customers came to you and you have to create models for all of them, you can do it in parallel. You are not limited by the size of your cluster. Basically, it works if you have peak loads, if you have to retrain regularly, let's say, models every day, and you want to train them on demand. Where it doesn't work, if you want to start and just make a prototype, you will be better off with SageMaker. It will definitely help you to start, like, to make the first mile into your model. Alternatively, if you have very complex model, and for training you require to have multiple GPU instances, you will have to create your own cluster, and you will have to use some high-level framework which allows to handle distributed training. So if you have this kind of complex model, batch won't save you. Same repository, I will show demo at the end of the presentation. And finally, machine learning, deep learning inference pipeline. Basically, it means that, for example, we want to deploy the model and see how it performs. So we want it to be scalable. We want to have like custom logic. So how usual architecture for deploying inference looks like? Basically, deep learning API. You start with Route 53 to have your API. You then load balancer, then cluster, where you obviously handle your instances from Spot and auto-scaling group, and you have ECR where you keep your Docker container. So it's like the most basic architecture it could be. And how it would look like in serverless way. As you can see, just API gateway plus Lambda. Model will be stored on S3. That's all. Alternatively, instead of API gateway, we could use SQS if you have a job queue, or you can connect it to Lambda and start step functions. Why would you want to use step functions with inference? Basically, you want to have, if you have different versions of the model, and you want to compare the results, and let's say you rolled out new version of the model, and in the end, you compare the results and see that it's too off comparing to old version of the model, then you can basically ship the old version result. So you can make this kind of like slow deployment. And also you can combine multiple frameworks. Let's say you can extract features using TensorFlow, you can train your model in PyTorch, and you can have pipeline which uses both. And finally, like if you want to import model, the usual ways you have to keep them in S3 and load them in the beginning. So it's different type of files depending on your framework. And specific pricing example. So inception of a tree model, it's image classification. So it's AWS Lambda, two alternative, 3 GB RAM, so maximum RAM, maximum CPU, and 1.5 GB RAM. So here you can see basically how different the price depending on whether it's warm or cold invocation. So difference is pretty significant. So one of the ideas is basically you always have to try to make as much warmer invocations as possible. Thing number two, as you can, although a 3 GB RAM provides higher speed, and basically you can achieve with warm container, warm invocation like 0.8 seconds, the issue here is that it will be more pricey if you would do the same with 1.5 GB. So you have to balance it. Although you will get speed, but you will also have to pay more. And some life hacks which allow to do that. Basically, try to store model in your warm container. In Python, it's global variable. Download model in parallel because when you have more than 1.5 GB on Lambda, usually like 3 GB of RAM, it means that you have two CPUs. So you can use threading and you can do things in parallel. Try to store a model as part of the library, and then you don't have to download the whole model. And the most hackiest way, but it's also very useful, is that if you can separate model in different layers and chain lambdas together, so one lambda produces features and gives it to another lambda, which then produces the prediction, it would be the best way if no one has to have download anything from S3. And obviously try to batch the workload as much as possible. So basically, when would it work? So if you want to have a pet project, it would be perfect because Lambda is a freemium service, so you have a lot of free invocations per month. If you want to make a simple MVP for your startup project, same. You can make a fast delivery to your customers. If you just want to use some pre-trained model and with easy infrastructure, so you don't want to care about it and want to move your startup domain name from .com to .ai, that's basically the best way. And if you have a simple model, and then this architecture will also help you, so you deploy something once and you don't have to care about it. And finally, if you have extremely high peak loads, then it would help you to handle it. And when it doesn't work, even like in perfect example for warm container, it's 0.8 seconds. It may not be enough if you want to produce real-time result. So, and you will be limited that a cold invocation could be pretty slow. Alternatively, if your model requires a lot of data, a lot of processing power, then you will probably have to use a cluster. And finally, if you have to handle a large number of requests, if they're peak requests, then maybe it's good with Lambda, but usually it means that you have to switch to cluster, as you get no economy of scale with Lambda. Two projects, basically with links, one is image classification using Lambda, so it's one thing. And the second project is accessible web, when basically it's image captioning, API which describes what happens on the image. Some repositories to check. Basically, this two contains prepackaged libraries for Lambda and Google Cloud Functions, including TensorFlow, PyTorch for deep learning, a lot of libraries for machine learning, image processing, text processing. So, conclusion, thank you. So here is the link to presentation, and now the time for demos. Okay, basically I deployed the pipeline beforehand. I just wanted to show you basically that the only thing you have to do is basically serverless deploy, and in one command it gets deployed from configuration file. I will show you, and it will produce you the link which you can use to trigger step function. So here is the link. Well, basically, let's try to create several invocations. Basically, it's just triggers invocation. Here is the dashboard. Let me make it larger. Dashboard with state machines. Basically, you can see it created 10 requests. We can have a look at each request. We can see where it currently is, and we could basically see the input and output for each step. So it provides a good way to trace your whole thing. Next, it basically created 10 requests to the AWS batch. Let's switch to AWS batch. As you can see, it created 10 runnable tasks, which it will try to, for which it will try to create cluster. Here it's EC2 dashboard. So as you can see, it created basically a cluster. It tries to create 10 instances of P2X large to run GPU workload on it. And as you can see, as I will show you right now with configuration file, it's very easy. So you don't have to manage any of it. And finally, there is a CloudWatch log, which allows to access specific log of what happens on within your batch process. So here is the repository which I mentioned. So basically, let's look at specifically deep learning training example. Basically, it has two folders: Docker with easy Docker file, because AWS provides a good image for GPU workload, and exec, which is just a Python file with fashion NIST example, and AWS batch. Basically, it utilizes serverless framework, which with step functions plugin and additional resources, where so basically you just define your region provider, you define your Lambda functions, then you just define your graph of step function execution. So basically, you can have a step for Lambda, and it will call Lambda. You can have a step for batch task, and you define, basically, you don't have to define much, you just define command. So here command is static, but you can define command based on the output of previous step if you want to customize it. Basically, it's a way to pass data from previous step to the new step. And finally, you can run some tasks in parallel as branches. To define batch, the only thing you need to keep in mind basically here is image URL, which is something like once you push the Docker image, you will get it and you will just need to update it here. So currently it uses like one of mine. Second thing which you need to keep in mind is to use like type of instance. And you can define bid percentage, which is maximum price you can pay for your spot instance. I put 100%, so it would work better. Alternatively, you don't have to use spot instances. You can use just on-demand ones, because let me check how good it works. Oh, it works better. Because so the issue with spot instances, specifically with spot instances in US East 1, that sometimes spot requests get failed, and because like you may not have enough spot GPU instances in the data center. So it's something you have to be mindful. And as you can see, it created the all requests and created a lot of GPU instances, basically 10 instances, 1 instance per job. As you can see, it completed all the tasks, so they're not in runnable state, they're in succeed state. And if we look at the function, you can see that it finished its execution. So basically, and you can see even like the history, you can see timestamps, all stuff. Now let's look at the inference part. Basically, here how Lambda with TensorFlow looks like. Here, like first I want to show you how it works and the difference between warm and cold container, and then show you the code. So here it just tries to classify image with Panda. So as you can see, first execution, it was called execution 3.1 seconds, 3.2 seconds. Now it will be the warm one. As you can see, it's a lot faster, 700 milliseconds. So you can see the difference is very big. So basically, but you have to keep your model in RAM. You have to keep a lot of things like in your memory and cache it between executions. So here's the repo with different packages for Lambda, basically which you can download and start using with your AWS Lambda. Specifically, I want to look at TensorFlow because it has the example which I show you. First of all, you have index.py file. Basically, that's the example. In terms of TensorFlow, for example, you would need to define session as global variable. example is here. And basically, it would mean that it would cache between your executions. Second thing is basically, if you want to build your own pack, it's pretty easy. So basically, you have a shell script which you can run within Docker container, and it will gather all necessary libraries for you. And for TensorFlow, it specifically has code which removes unnecessary folders and unnecessary libraries, and compresses some shared libraries. Okay. Thank you very much for your attention, and if you have any questions, I would be very glad to answer them.
I've noticed there's some effort to make Jupyter work more with serverless or with changing the RabbitMQ. I see some work in Jupyter to change the RabbitMQ to like SQS or something. I just saw a little bit, and I was curious about, have you thought about that at all?
Well, Jupyter, like if we're speaking about like process, Jupyter is part of like the first process when you try like to train model locally and try to get first architecture. And I think RabbitMQ is basically very similar to SQS, but the issue is that SQS isn't open sourced. So basically, you cannot start SQS anywhere other than within AWS. So.
When preparing your data for processing the machine learning, how much percentage-wise is or work involved for preparing the data?
Heavily depends on specific cases. Like I would say, I previously give an example. I worked in previously in company which uses satellite imagery, and it required a lot of pre-processing basically because you have like very raw data which you have to process, you have to gather it, and so on. With text, it may be less so, but so basically usually you have to do a lot of things with images because you have to align them if you train something. If you want to classify, or you usually have to crop it so it has the same size. You have to align it so it looks in the same way. So there could be a lot of pre-processing for images, if that answers your question.
Thank you. Just now you mentioned that Lambda may not be suitable for the real-time request, right?
Yes.
Near real-time. So how you define the near real-time request response? So like how many milliseconds or second level?
Well, if you want to achieve real time, the best you can do is to have like GPU cluster, because inference will run pretty fast when you have GPU. So if you basically you have to have GPU cluster, you will have to have like GPU cluster with ALB with load balancer, and in cluster itself you will have to keep model in memory. And then it will be easy to achieve under half a second, like 100 to 200 milliseconds for usual kind of model.
Okay. So you define the near real time is maybe less than 1 second?
Yes.
Okay.
Are there any more questions? All right, let's thank our speaker.